Welcome to today's talk on elastic collisions and the conservation of momentum. What are we learning? What is an elastic collision and how to calculate quantities in elastic collisions? First, an elastic collision is where objects bounce off of each other. We'll see that momentum is conserved in an elastic collision, as is kinetic energy. It is also conserved. In an elastic collision, we'll take two masses. This is mass number 1, mass number 2. The masses will collide with each other. They'll have a velocity before the collision. This is the velocity of mass 1, initial, or before the collision. This is velocity of mass 2, before the collision. We're also showing our coordinate system here. These two objects will collide. After the collision, they'll bounce off of each other. This is the velocity of mass number 1 after the collision, or V1 final. This is the velocity of the second object, or V2 final, after the collision. If we take these two objects as our system, and we say that this is an isolated system, the momentum of this entire system will be conserved. What that means is that it will not change even though there was a collision. So if we add up the momentum of mass 1 and mass 2, just by going mass times velocity, this is the momentum of the first object, and add it to the momentum of our second object, it will stay the same. Also, with an elastic collision, the kinetic energy, the total kinetic energy, here is the kinetic energy of mass 1, which will be 1/2 mass 1 times velocity 1 initial squared. Here is the kinetic energy of mass 2. The total kinetic energy after the collision will be the same as before. So here's a problem-solving strategy for one-dimensional collisions. First, choose a coordinate system. In this case, we are only doing a one-dimensional collision, so we just need to decide which direction is positive and which direction is negative. Then draw our diagram of our objects. Use the conservation of momentum principle, which will tell us that the total momentum before the collision is the same as the total momentum after the collisions. Only for our perfectly elastic collisions will the conservation of energy work. In that case, we can simplify our conservation of energy equation to the initial velocity of our first object minus the initial velocity of the second object, equaling the negative of the difference between the final velocity of the first object and the second object. And of course, then solve for whatever missing variable you have. All right, let's try an example problem. Let's say that Jeannie rolls a 7-kilogram bowling ball down the alley for the league championship. One pin is still standing. Jeannie hits it with a velocity of 9 meters per second. The 2-kilogram pin acquires a forward velocity of 14 meters per second. What is the new velocity of the bowling ball? All right, so we are expert physics problem solvers now, so we know what to do. We are going to start drawing our diagram. All right, so we have two masses, the bowling ball and the bowling pin. The bowling ball has an initial velocity. The bowling pin is at rest. They collide. The bowling ball continues, we think, in the same direction, and we're going to call this positive, x positive. The bowling pin had a forward velocity that was given to us. Speaking of which, let's write down everything that was given to us and what we're looking for. The mass of the bowling ball was 7 kilograms. The mass of the bowling pin, 2 kilograms. The initial velocity of the bowling ball, 9 meters per second. The initial velocity of the bowling pin, 0. The final velocity of the bowling pin is given as 14 meters per second. So how fast is our bowling ball going afterwards? Now let's write out our equation for the conservation of momentum. We're going to add the momentum of the first object to the second object, and that should equal the momentum of the first object and the second object after the collision. We're saying that this is an isolated system. Since our initial velocity of our bowling pin is 0, that means that this is 0 here, meaning that this whole part here, this M2 times 0, that's going to be 0. So we can just get rid of that part. I'm going to rewrite this without it. So what are we looking for? V1 final. Here's V1 final. We don't know that. We can find that by solving this whole equation for V1 final, which means I'm going to subtract M2 V2 final from both sides. I'm going to flip this around also to put what was on the right on the left and the left on the right. We're still looking for V1 final. It's multiplied by M1. We can divide M1 by, on this side. We can divide M1 on this side. And we're going to finally have our equation. Now we're ready to go. All we have to do is do the plug and chug here, put all of these quantities in their correct places, fire up our calculator, and get our answer. All right, so our bowling ball was then going 5 meters per second. This came out positive, so it's definitely going to the right. Let's summarize what we know now. First, using conservation of momentum for elastic collisions, where we have two objects with initial velocities that are going to collide and bounce off of each other. The total momentum before the collision will be the same as the total momentum after the collision. Also, the total kinetic energy will be conserved. This means that the total kinetic energy before the collision will be the same after the collision. Rewind and review as necessary. Don't forget to complete and turn in your Cornell notes, and thanks for listening.